Hi and welcome to section 4, Implementing the Analysis Tier. This section will contain a deep dive into the analysis tier principles and it will mainly focus on Apache Spark. For start, let's dive into the analysis tier headlines. In this video, we will cover the main conceptual aspects of an analysis tier. So let's start with the analysis tier overview. The analysis tier sits in the middle of our streaming pipeline. It is the superstar of the pipeline since it is the only tier that contains business logic for processing the data, while the rest of tiers are used to transport or store the data. In our case, the analysis tier will be Apache Spark, and it will ingest data from Apache Kafka and publish the results in MongoDB. But let's take it step by step and let's start by discussing about the continuous query model. In order to understand the meaning of continuous query model, let's assume that the analysis tier should be capable to analyze or query the data from a database. The traditional approach will imply executing a query over the available static data. This means that the analysis tier will receive a result set that matches the executed query. This result set can be all data matching the query or a slice of data depending on how the query was built. But remember that another tier, for example the collection tier, must load the incoming data in the database. And since we are in a streaming pipeline, the ingestion rate can be significant. In order to deal with this ingestion rate, the analysis tier must repeat the query, for example at every 5 seconds. Another approach consists in triggering a new query immediately after the current result set was processed. The main drawback of these approaches consists in the fact that we cannot react in real time. And this is why, in a streaming system, the queries are embedded in the analysis tier, and they represent streaming algorithms commonly written based on the API specific to the chosen analysis tier technology. At first sight, this may look unusual, but let's add a few headlines to this approach. First, the data flows continuously and endlessly through the streaming algorithms in real time. Since the streaming algorithms are actually the queries, we call this the continuous query model. In order to analyze the data, the analysis tier pulls data from the message queuing tier as fast as possible, but not faster than that. This means that the message queuing tier is capable to serve data in real time and eliminates repeatable queries and potential back pressure. Another important aspect of a productive analysis tier is the fact that the continuous query model runs in a distributed fashion. Let's assume that our analysis tier runs on a single machine, so the collected data is analyzed on a single computer capable to run our continuous query model, or in other words, our streaming algorithms. Now, the metrics of our stream processor may reveal if this is working fine or not. In other words, depending on the computational capacity of the machine and the complexity of our streaming algorithms, we may not be capable to handle a certain amount of data and speed of ingestion. This means that the vertical scaling has reached the limits. Sooner or later, this machine will become the bottleneck of the pipeline, or even worse, it will cause a failure. Well, the solution is to take advantage of horizontal scaling and run the analysis tier on multiple machines in a distributed environment. Generally speaking, independent of the analysis tier technology, a distributed streaming processor involves 3 main components. First, we have the application driver. With some streaming processors, this will be the client code that defines the continuous query model and communicates with the streaming manager. The streaming manager has the general responsibility of getting your streaming job to the worker nodes. In some cases, it will control or request the resources required by the worker nodes. The worker nodes, also known as task managers, task runners, stream processors, or simply workers, are responsible to get the job done, to apply the corresponding streaming algorithms to the ingested data. The data sources represents the input and potentially the output data from your streaming job. In some cases, you may want to collect the data back in your application driver and use it as an input for another streaming job. In other cases, you may want to write it out to a different data source, like a long-term storage, to be used by another system. Some of the most popular distributed streaming processing systems include Apache Storm, Flink, Samza, and Spark. Pretty soon, we will deep dive into Apache Spark, but for the moment, let's have a brief overview of the high-level architecture of these four systems. And let's start with Apache Storm. Apache Storm, in simple terms, is a free and open-source distributed framework for real-time processing of data streams. Let's briefly overview the Storm high-level architecture. Its high-level architecture relies on Nimbus master node. Nimbus is responsible for distributing code around the cluster, assigning tasks to machines, and monitoring for failures. Each worker node runs a daemon called the supervisor. The supervisor monitors the work assigned to its machines and starts and stops the worker processes as needed. Each worker process executes a subset of a topology. A running topology consists of many worker processes spread across many machines. Finally, the coordination between Nimbus and the supervisors is done through a Zookeeper cluster. So, this is how Storm works. Apache Samza is a free and open source near real-time asynchronous distributed stream processing framework. It uses Apache Kafka for messaging and Apache Hadoop Yarn to provide fault tolerance, process isolation, security, and resource management. Let's see the Samza high-level architecture. Yarn is a cluster manager designed to handle resource management and job scheduling and monitoring. Here, the Samza Yarn client is responsible to request the Yarn Resource Manager to allocate resources for the Samza application to run. The Yarn Resource Manager is responsible for allocating resources, CPUs, memory, disk, network, and so on for all the applications running in this cluster. After the proper resources are allocated, the Samza task runners are executed on different nodes in the cluster. Well, another important player is Apache Flink. Apache Flink is a free and open source distributed, high-performing stream-first framework where everything is viewed as a stream. The core of Apache Flink is a distributed streaming data flow engine capable to deal with two building blocks, streams and transformations. Let's see what are the coordinates of Flink high-level architecture. First, we have the Flink client and our application or streaming job. The Flink client is responsible to optimize the job, construct the job graph, submit the job graph to job manager, and retrieve the job results. The job manager is responsible to create the execution graph or parallelization of tasks, to assign the tasks to task managers, and supervise the execution state. Finally, the task managers are responsible to run the assigned tasks. And we finally reach out to the stream processor that we will use, Apache Spark. Apache Spark is a free and open source high-performance framework, general-purpose distributed computing system. Since we will deep dive into Spark in the next videos of this section, we will skip the overview for now. So every time you need to choose between these stream processors, consider this table, which is a head-to-head comparison between their main skills and features. Further, let's discuss about the main features of a streaming framework. We start with the delivery guarantees feature. First, at most once. If for any reason a message was not processed by the worker node, then it is lost forever. This is the simplest delivery guarantee. At least once. If for any reason the streaming manager concludes that the message was not processed, then it will resend the message. In this case, the messages cannot be lost, but may be redelivered. So your streaming job must be idempotent. And exactly once. In this case, the messages will never be lost, and they will be processed exactly once. This is the most complex delivery guarantee, and worker node must respond with a success or failure after a message is processed. Another important feature of a stream processor is state management. Complex streaming algorithms may rely on previous processed data, so they rely on state. In other words, the current data or task cannot be processed individually. It may rely on previous processed data coming from the same stream or even other streams. And in this case, the framework must be capable to hold and manage the state of data. While a stateless stream processing action contains only some input and output, a stateful stream processing action requires a state that the worker node can access via input and output operations. This way, the worker can store or fetch a certain state. The simplest approach for providing state relies on using the memory of the current worker node. For example, here we count the user actions by type for 1 hour by holding the counter's state in memory. Our streaming algorithm is just a filter operation capable to update the counters based on their previous state. But using a memory state can cause serious issues like losing the data. So use this approach only when the risk and possible loss of data is acceptable. When you simply cannot afford to risk of losing data, it's time to rely on replicated, queryable, persistent storage. Besides avoiding this risk, we also can take advantage of joining multiple streams. This way, we can provide complex analysis of the current data based on a multi-stream state. Finally, a stream processor must be fault tolerant. This is a must because we have at least 7 points of failures where we can lose data. First, we can consider a failure of the input data source, which normally is the message queuing tier. This is not under the control of the stream processing framework, but the framework must be capable to respond gracefully and not fail if data or the resource is not available. Second point of failure can take place at the network level. The stream processing framework cannot control this kind of failure as well, but it needs to handle the disruption gracefully. When the application driver just submits the streaming job to the streaming manager, there is no risk of failure. But when the application driver logically contains the streaming manager, it is exposed to the same risk as the streaming manager. If the streaming manager fails, then our analysis tier will look like a chicken without head. This is known as running headless. For a while, the worker nodes will continue to run without being supervised. Nevertheless, with no supervisor, we cannot start new workers or recover those that will fail. Well, workers is the place where our code is running, and it should be under the supervision of the stream processing framework. If something goes wrong here, then the streaming manager should take steps to restart the worker or move the processing to a different machine. Failure point number 6 is related to the connection to the output destination. In such cases, failure of the network or destination is unavailable. The stream manager should be capable to control the flow of data in order to avoid to overwhelm the workers. Number 7 is not under the direct supervision of the streaming manager, but its failure could impact the processing of the stream, so it needs to be considered. Having so many potential failure points requires some robust approaches meant to keep this risk under control. Two of these approaches are state machine and rollback recovery. Both of them can be employed for enabling replication and coordination of a stream processing system. More precisely, we are talking about replication and coordination of the streaming jobs, which are basically the units of work that manipulates the data. Both approaches assume that we have designed and thought about our streaming algorithm in an idempotent way, meaning that they always produce the same result. More precisely, for a streaming job to be idempotent, it means that two non-faulty workers that receive the same input in the same order will produce the same output in the same order. The state machine approach handles fault tolerance via replication. It should be capable to ensure that replicas remain consistent and that replicas process requests in the same order. These are the responsibilities of the stream manager, which ensures replicas consistency by replicating the streaming jobs on independent nodes, and it coordinates the replicas by sending the same input in the same order to all. In the second approach, rollback recovery, a distributed system is like a collection of processes over a network. Rollback recovery should periodically save the state of processes in a storage. This allows to a failed process to restart from a saved state. A saved state is called a checkpoint. In this approach, a worker node periodically wraps the state of our computation into what is called a checkpoint, which is copied to a different worker node or on a non-volatile support such as a disk. Between checkpoints, the worker node has to keep track of the computation, but in case of a failure, it can recover from the most recent checkpoint. As you will see soon, Apache Spark relies on checkpoints. Well, for this video, we have covered every item from the agenda.